logged in from elsewhere listening.
Okay. All right. Welcome, everybody. Thank you for coming to today's seminar. It's a pleasure to welcome Dr. Mahoney, Michael Mahoney, who is at the University of California, Berkeley, and affiliated with the Department of Statistics and the International Computer Science Institute. His work actually is very well cited and very well known in algorithmic and statistics and social networks, and maybe I should say just large-scale data analysis in general. He did a lot of work on linear algebra, matrix, and randomized numerical linear algebra. I mean, you name it, he's done it. He received his PhD from Yale in computational statistical mechanics. He's actually a physicist by trade. And he's worked and taught at Yale in math, and was also worked for Yahoo Research, and was also at the Stanford Statistics and Computer Science departments. And he's on the National Advisory Committee of the SAMC, which is our own baby here, regional baby. He was also on the NRC committee for the analysis of massive data. He runs the biennial MMDS, which is actually quite well-known workshop on modern massive data sets. And he's now involved in the organization of the Simon Foundation program, the Theoretical Foundation of Big Data Analysis. And so he's the right person to have here today. It's a pleasure to have him here. He'll be talking to us about his work on social graphs. And thank you for coming.
All right. Well, thanks for having me.
The floor is yours.
All right. Well, thanks for having me. It's good to be here. So social networks is something people, like to think about and talk about. And what I want to talk about is tree-like structure. And I mean, the first thing, it's not obvious there's anything to say, right? Because trees are a certain type of graph, and they're basically a graph with no loops. And from day one, the page one of the introductory social network book, if you go to it, you'll learn. You don't even open the textbook. You learn that friends of a friend become friends, right? So triangles close, and there's lots more complicated structures. So what, if anything, does trees have to do with that? So hopefully by the end of the hour, you'll see that trees actually have a lot to do with that, but in ways that are a little bit different than one might naively expect. So that's what I'd like to cover basically. And let's see how we can do this. All right. So I'll try and convey sort of the basic idea. There'll be a lot of pictures that look like this, nice pictures. And some of them will be suggestive, and some of them will be suggesting the wrong thing. And you should ask yourself, what does this picture tell you, if anything, about the graph? So if it's a road network of the U.S. on the bottom left, and that tells you something about the geography of the graph, maybe, that there's an east coast and a west coast and so on. But what if I have an arbitrary social graph? What do these pictures tell me? And what insight can you get from them? So that's going to be sort of a theme we'll be talking about. And it's not such a huge room, and so basically I want to, if there's things that aren't clear, someone should holler. Basically because there's three things you need to know by the end of the hour, and the rest is details. Now the details are going to be important if you want to do anything, but if you sort of don't get the basic ideas, then you just get lost in the weeds of the details. And so the basic ideas are going to be that real graphs have very, very different properties than most of the data sets. And a lot of that has to do with local properties in the graph versus global properties in the graph. All right? So by local properties, I'll mean things around you, a given node. By global properties, I mean things that depend on the whole graph. So if you think of interactions between people on the Earth, what about you and your 100 closest friends versus you and your 7 billion closest friends? What's the properties of the graph look like? And that matters, one, because if you're worried about disease spreading, how well is it connected? But also, if you just run algorithms on the graph, Spectral algorithms are about diffusions, basically, and so you don't even need to think about the disease modeling. If you just want to run an algorithm, the algorithm is doing certain things, and you can ask yourself, what is that algorithm doing on this graph? So the local properties and the global properties are going to be very, very different. And what we'll see is that by understanding certain coarse and fine-scale properties, the graphs will be tree-like at large size scales in certain ways. So the motivation here is that graphs appear in all sorts of places. Lots of methods for understanding very large-scale structure like diameters and degree distributions and things. Stuff for understanding small-scale structures, clustering coefficients, which is probably the triangles close. There's not a lot of tools for understanding what I'll call intermediate scale structure. 5,000 nodes, 10,000 nodes, 100,000 nodes. And you can tell yourself a story, maybe small clusters cluster together into bigger clusters, and there's some hierarchy and so on. That's an empirical claim. Maybe it's true, maybe it's not. Could you test that empirical claim? If it's false, it still might be a useful way to model the data. Right? Naive Bayes is false, but it's sometimes a useful way to model the data. If it looks like it's sort of true, the question is, are the algorithms you're actually running, or the heuristics you put on top of those algorithms, sort of respecting that structure or not? So that's going to be something we get back to. So basically, we want to develop tools to understand and exploit this intermediate scale structure. So go one step beyond you and your 3 or 4 friends to what's going on, around you. If there's a cluster that you think is Raleigh and the cluster that you think is Durham, could you find that parent cluster by running some algorithm? Or is it the case that parent cluster is a little bit more diffuse than each particular cluster, and by the time you start to get beyond the Raleigh to try and flesh out the Durham cluster, 3 steps later you're touching the whole world? And so if you can find it, that's good. If you can't find it, but you run a black box that you don't quite know what's going on because the graphs are meshy and non-visualizable, what are you going to get? And so that's going to be something. So can we develop tools to try and pull that out? Oh, yeah, keep. OK. So this is what these graphs look like. So what do social graphs look like? So they don't look like road networks or things nice. They look sort of like some hairball. And so we use some visualization algorithm here. We could have used a different one. It would have been equally non-informative. All right? So people develop lots of models, hierarchy and small worlds and core-periphery. So I think it's a fair question before we get started to sort of say, who cares even what these graphs look like? Because what we want to do is get tools to understand the intermediate scale structure. And for that, we need to have some sense of what they look like locally. Just take this graph as an object. That's some interaction between people. And what does this graph look like if I'm looking at the Raleigh area and the Durham area? And how does that interact with the southeast U.S., the rest of the U.S., the rest of the world, in sort of a qualitative sense? So who cares about that? So first of all, it's sort of helpful, I think, for getting intuition. There's a lot of people that munge with data and sort of want to have a rough idea of what the data look like. Degree distribution and clustering coefficients do that, but can you get better and more robust versions? It's going to be important for controlling inference. So there's a range of ways people control inference. It has to do with typically some sort of isoperimetry. You want there to be a lot of stuff going on here, not much going on there. That has good algorithmic consequences, but also means if you have information here, you can make good predictions here and not be contaminated by there. And so you want to control inference. It's helpful for developing sort of non-trivial theory. If you just like theory, what if I have an algorithm and I returned you a log n approximation to all distances, all pairwise distances in the graph? Is that informative or not? So for a general graph, the answer is definitely yes. If the graph has diameter log n, the answer is no. Right? Here's a faster algorithm to get a log n approximation to all the distances. All the distances are 7. Right? If the diameter is log n, that's a good approximation up to some log n. Right? So why run something that takes more than the 1 step, return 7? So if you want to get non-trivial theory, but maybe you don't care. And some people that don't care. So there's applications where you want to do 0.1 or 0.01 or 0.001 better predicting some quantity, click-through rate, for example. And those typically correlate with applications where sort of the meta information is more important than the graph itself, the graph structure per se. So there's applications, in particular social network applications, where you suggest, here are people you might know. Do you want to add links to them? And if the answer to that is yes, what the service is doing is basically encouraging you to add more links that might damage the graph structure per se because it wants to harvest meta information. And so you might not care about what they look like. But if you do, that's what we're going to be talking about today. So people think about networks. So there's a million ways to think about these things. Today I'll talk about the simplest model, the so-called interaction graph model. It's just nodes and edges, nothing more. You can add directedness, you can add weights, you can add time, you can add lots of other stuff. A lot of what I say will go through to that, some of it won't, and that's going to be a complicated space. But let's just work with the simplest thing. Why? People barely understand the simplest thing when you actually get down to the nuts and bolts of what real graphs look like. So let's work with the simplest thing, then we'll get more involved. And the first thing to know is, graphs are combinatorial, not obviously geometric things. So if you're asking for a local struct that's geometric or metric or tree-like, I mean, what are we doing? It's not obvious that we can do anything here. So it will turn out that we can, but geometry is oftentimes used for inference, and so that's why it's will be of interest. So there's going to be lots of networks out there. And one question is, if you develop a tool, then you're an algorithm. You're not a method. You're a methods person. You develop any algorithm. I have a new graph from a different domain. I give it to your algorithm. Your algorithm doesn't know where this graph came from, right? It's just a graph. And so you run an algorithm, you get an answer. So I'll be taking the approach today where we'll be talking about the structural properties of the graphs. And these graphs will be generated from a bunch of different applications. And so if you want to instantiate these ideas in any particular application, usually every particular graph or every particular application is going to be a little bit of an exception to the sort of simplistic story I'll be describing today. And we have a reasonably good understanding of where that's the case in most cases, but not all. So for example, it's clearly the case that social graphs are different than biological graphs, right? If you have a genetic network of interactions between proteins. But in a lot of cases, you're going to get tight clustering between a small number of proteins. If you have clusters that have a huge number of proteins, they're going to be sort of amorphous and diffuse. At that level of granularity, that's true for most of the other graphs on this page, right? And so can we get information with the local structure and the global structure independent of where the graph came from, but you want it to be interpretable for the domain scientists so that they know what it looks like, so you can map it back to that understanding. So but just to give you a little bit more sort of idea of at least where we've stress tested these things, most social information networks are very nice because they're very sort of bad in a lot of ways. Most of the assumptions you might want to make, either algorithmic or statistical niceness assumptions about the data, are just sort of manifestly false. And so this is a set of graphs, it's a subset of the things we looked at in the original study on large-scale networks 6 or 7 years ago by now. Live journal, social graphs, e-opinions, Flickr, so on, citation networks, collaboration networks, blog cross-postings, a bunch of these sorts of things, sort of broadly social and information type networks. Every graph is going to be an exception to the simple story I'll be talking about. But first of all, sort of look at this for a second. What's going on here? We have 4 million nodes and 40 million edges. So incredibly sparse, by any sense of the word. And probably pretty noisy. Why do people add links on live journal? It's just because someone sent you a link and said, will you link to me? Not for particularly strong reasons, right? So you can imagine there's a lot of noise. Now, sparsity and noise are sort of meaningless words in the sense that everyone uses it and means different things with them. But in this context, we're going to try and map it back to graph theoretic notions. And sparsity means something in a graph. It means sparse. Noisy essentially is going to mean random or quasi-random. And so you can ask, what are the properties of extremely sparse random graphs? And we'll see that a lot of the local properties and global properties there are going to be informative for what's going on in the real data sets. Clearly not naively or stupidly, but as a qualitative guide. And so, for example, it'll turn out the 0th order bit to describe a lot of these graphs is that they look like extraordinarily sparse random graphs. Now, in extraordinarily sparse random graphs, triangles don't close, right? So can you map those two together? Can you get some way to get some sort of local structure, map it to some sort of global structure, where the global structure looks like this extremely sparse thing, but the local structure looks like you and your 100 friends? And that's sort of the tools we're trying to develop here. All right, so let's see. Popular approaches, you define simple statistics that typically are very, very local or very global, degrees, clustering coefficients, and just sort of fit models. So if you want to go beyond very simple statistics, density of a graph, a little bit softer, diameter, routing, clustering, communities. A lot of these have to do with intermediate scale structure, right? You route from here to there, you need to go via somewhere, and there's probably better and worse ways. Oftentimes you want to go from a local neighborhood to something global, you've got to go via intermediary and then back to some local neighborhood, and that's the structure of most of the work there. So it turns out popular models just essentially fail rather egregiously when you consider these sort of more refined notions. So what do you mean by that? So algorithmic decentralized search. So Kleinberg, so there's the Milgram experiments, Watt-Strogatz small world model. The idea is, I give you a postcard, you have to get it to some stockbroker in England or Boston, sending it to people you know. So, half of these things found their way there. And so Watson-Strogatz developed the small world model, and Kleinberg said, well, in fact, there's a much stronger result in those empirical results. It's not just that there existed these short paths, that people actually found them. And the model, the simple model random graph models that Watson-Strogatz had, even though they had a local geometry, so they got triangles to close. Basically, any random graph will have a small diameter. And so that fails to account for this algorithmic property that people actually found them. How do you find them? You can start with some geometry and add edges in a very careful way, where the probability that you link from there to there depends in a very sensitive way on the local global coupling. Diameter and density versus time. all these graphs are time evolving. You can say, how does the density behave in time, and how does the diameter behave in time? Essentially, all the random graph models, the diameter grows to something like log n. So slowly, but not too much, but increases. Empirically, Quebec and Kleinberg and Falutzos in 05 or 06 showed that the graphs densify and the diameters shrink. So that's just an empirical fact about the world, about the graphs. And you can say, do any random graph models reproduce? And the answer is no. So they introduced a bunch of models, some of which are more and less realistic. The most realistic one was able to reproduce the densification and shrinking diameters, but did so by doing it what they called a forest fire model, but it was a particular instantiation where there's a very sensitive dependencies on how they burnt new nodes, basically. And so you had to get that coupling right, and in a very sort of sensitive and non-robust way to couple the local and the global. Clustering community structure. So this is something that we did. Yuri was Leskovic was an intern. I was at Yahoo at the time with Lang and Dasgupta, and said basically, I was a matrix person there. They came and said, are they good? We're getting strange results applied to these graphs. Why is that? And they were getting strange results, and they were sort of for very fundamental reasons. It's that essentially most matrix algorithms assume certain global properties. If you do low-rank approximation, if you do spectral approximation, you think the data is split well. You have some number of clusters. Empirical question, are there good clusters in these graphs? Answer, no. Now, of course, how do you answer that? There's a million definitions of clustering. Certainly there are definitions of clustering such that you can find one of these graphs such that there are good clusters. So clearly, making a stronger claim like that, there's a lot of bells and whistles. But the answer is there's not good clustering by what people typically mean. Now, that matters if you care about clustering in communities, but it also matters if you run algorithms, because algorithms have implicit assumptions that go into them, namely when they're sort of more right and less right to use. And if you're running an algorithm that's assuming something implicitly different than is going on in the graph, you're going to have problems. All right? So all of these have to do with some finer notion of coupling between local and global structures. So that's where the trees are going to enter, and that's what I'm going to talk about mostly today. So why tree-likeness? And then I'm going to take a slight detour. So why tree-likeness? So a lot of work suggesting graphs may be tree-like. So hyperbolic geometry. So there's work on routing where you say, I want to put the graph in a negatively curved space. So if you don't know what that means, think map of the Earth. The Earth is positively curved. It's a sphere. Alaska's bigger on a flat map. Right? Alaska's bigger on a flat. So informally, there's sort of more area on the flat map than there is on the sphere. So if you go to negative curvature, it's like a saddle. There's more volume there in some informal sense. So back to the analytics, what does that mean? It means if you change the curvature parameter, you can just hide lots of stuff there. You can fit anything you want. And so you want to change the curvature parameter in such a way that you can do something useful and not overfit the data. So most of the work here has been done on routing, which allows you to find short paths, but there's been another one, in particular geographic routing. So there's and so they use that hypothesis to get better routing properties. The lack of large-scale community structure, not obviously what that has to do with tree-likeness, but informally, you want to say if a graph is expander-like, meaning it doesn't have good clusters, but has other structural heterogeneities, for example, degree distributions of things like that, those structural heterogeneities might provide a scaffolding on which the graph can be tree-like, and we'll talk a lot about that. Some theoretical work, some stuff on visualization. I have a big graph, and I want to do some fisheye view, and that's related to this issue about more volume. You can zoom in or zoom out and look at different. So a lot of work in visualization using tree-like properties. All that being said, if I give you a graph and I say run any of these tree algorithms, you're going to be hard-pressed to find stuff because there's just lots of noise and lots of junk. Some of these are statistical hypotheses. Some of these are just visualizations and people sort of mess about. So if I give you a graph and you just try and run a tree algorithm, you're going to have some difficulties. So can we do a better job with that? So background, before I get to notions of tree-likeness, there's going to be two different notions. One is going to be delta-hyperbolicity. One is going to be tree decompositions. And then I was going to talk about connections with prior work. I want to pull the connections with prior work up front because just talking to people today and yesterday, I thought maybe it would be a little bit helpful to do that because this is going to be the background that you sort of need to know. And okay, connections with prior work. Okay, so here's the prior work. This is work before about a year or two ago. This is with a bunch of people, but it's sort of centered around the large-scale analysis I referred to earlier. The tree-like properties I'll be talking about today, that I'll get to in a minute, are with a student, Aaron Adcock. And if you have any questions, I'm here today, but you're in luck because a lot of this was with Blair Sullivan, who's over here. And so if you have questions about what we actually did, that you think of this weekend. She's the one to talk to about that. But this prior work is sort of predates that and isn't tree-like per se, but is the background on the empirical properties that you need to know about in order to understand what we're doing with the tree-like structure. So what does a graph look like? So take a step back from the weeds and say, sort of, what does it look like? So, one thing a graph might look like is a hot dog. All right? And this is Zachary. If you know anything about social networks, everyone studies Zachary. And Zachary is a hot dog. By that, I mean there's a left half and a right half. And you can cut Zachary in the middle. And you bite the hot dog in half, right? And a pancake is like a hot dog, right? It's just a round hot dog. You can cut it in half, eat the left half and the right half. All right? It might just be a blob. It might be an expander, a 3 regular random graph. But there's no good clusters of any size. There's no way to cut it up in some nice way. If you try and bite it in half, you don't get much meat because half the stuff is on the surface of the hot dog. So we'll get back to what that means. But there's not a nice partition between the left half and the right half. It might be a tree in some sense. So I don't know how well you can see the bottom, but the bottom's a tree. The top is some sort of visualization of a real graph that we'll get to in a little bit that might be vaguely tree-like, right? There's some core and some stuff that sticks off. So squint at the graph. Don't worry about objectives and so on. What are ways that the graph might look like? It might look like a hot dog or a pancake that you can cut it in half. This thing you can cut in half by cutting one edge, but it doesn't really look like a hot dog, but there's maybe some hierarchy or something. And, this is a clique. It's a sparse. It could be a clique. An expander is a sparse clique. A constant degree expander is a sparse clique. So it could be that, in which case certainly not tree-like, but not well partitionable either. So say you want to find the best fit of an adjacency matrix. So don't worry about objectives or whatever. Just qualitative, the best fit of an adjacency matrix of a graph. How will this look like? And so you have alpha, set of nodes talk to itself. Gamma, the other set of nodes talk to itself, and beta is the cross term. And typically what you want to say is alpha talks to each other well, these guys, beta talks to each other well, and the cross term's less. And if alpha and gamma, I guess, are large, and beta, the cross term, is small, you're going to get something that informs your intuition, right? This is a hot dog or a pancake. There's a left half and a right half. You might have something that's sort of like an expander, right? That's all equally bad, and if it's a clique, it's all equally dense. There's other structures you can have that, bipartite and other stuff that will be relevant but not directly relevant today. But, it might be the case that alpha is large. Namely, there's some sort of notion of core. And when I say large, it might be marginally larger than small, but large in some sense. Beta, the crosstalk between the sort of core-like piece and a periphery, is medium, and the periphery talks to each other itself very little. These are sort of ways graphs might look. So a key thing you need to understand is something called conductance. So conductance is it's a combinatorial notion that has sort of a physical interpretation. And it's what I'll call a surface area to the volume. So if I have a big graph and a set of nodes, the conductance value of the set of nodes is basically the number of edges inside, some function of the number of edges inside, the size of that set. And some function of the number of edges crossing between that set and the boundary. So there's a boundary term, and there's a surface term, and there's a volume term. So call it surface area to volume. It's a combinatorial notion of surface area to volume. If people study communities, they say communities in social graphs are sets of nodes that have more and or better internal connectivity than they have with the rest of the world. There's two criteria. There's an internal connectivity. These are the amount of stuff inside. There's a question about connectivity with the rest of the world. There's a volume and a surface area. All right? The combinatorial thing that captures that best is conductance. It's imperfect, very imperfect, but that's the thing that captures it best. So that's what we'll be talking about. If you define modularity, you think large clusters are good up to second order. If you define other things, you think something else is good. So the question about what a community means is a separate question, but this is a structural property of the graph. Now this is of interest, one, because you can ask questions about the graph, but two, a wide range of machine learning tools boil down to this. If you do low-rank approximation, you believe you can put the data in a 10-dimensional space. Think latent semantic indexing. You believe you can put the data in a 10 or 100-dimensional space, and if you're in some 10 or 100-dimensional space, you can partition it in half. There's a left half and a right half. All right? If the graph doesn't have any good clusters because it's an expander, that's false. And so the question is, how does it actually look? So this is the way to measure it. Because the conductance of a set of nodes is a surface area to volume. The conductance of a graph is intractable to compute. It's the conductance value of the best set of nodes in the graph. That's intractable. There's a bunch of ways to approximate it, and in particular, spectral methods. we're going to ask a slightly finer question. We're going to ask for the conductance value of the best cluster of size k. So the conductance of the best cluster as a function of size. Not obvious what this has to do with trees, but we'll get to that. Fix the graph.
Okay. If you compute this as the graph grows, you can compute this initially and then start making updates. When does that fail?
I can give you lots of. I'm going to describe 3 classes of graphs and think of. That's the way the world looks.
Yeah.
Basically, that's the way graphs look. I can give you lots of strange examples of adversarial ones that behave in ways totally bizarre with respect to this metric, but they're very non-robust with respect to real noise.
Right.
The growing issue I don't think matters as much because a lot of the relevant parameters are going to depend on log n, and is 10 or 20 or 30 log n, or is it a half times log squared n? So it's hard to answer these questions about growing.
The n is a function of time also, that I don't want to go off and say, here's a picture of the internet today. I
Right.
want to say, here's a picture of the internet 25 years ago,
Yeah.
and 25 years plus a day, and 25 years plus 2 days, and see how it grows, and I can make these estimates, I think.
So ask that question at the end,
Okay.
because typically it grows locally.
Yeah. Right.
I know you, meet your friend, something like that. So it's not a global phenomenon. And so understanding the intermediate scale structure is important, right? Because I infect you with Ebola or whatever, and if you have no friends and you live in a cave. No, and it's going to make a big difference if you live in a cave versus you live next to Britney Spears or something, right? So, was that Britney? So the question about the local global coupling is exactly that. And the time varying we have a lot of ideas on. The problem with time varying is where's the ground truth data? I mean, the data we have is noisy and messy. There's a few examples, but not enough to do a large-scale systematic study like we've done here yet. But that's something we have ideas and results on that are related to the tree-like properties. All right, so before we get to this next slide, let me ask, say that you're a hot dog. Let's see if I can do this right. So say you're a hot dog. And I want to plot this conductance as a function of size. And this is phi k. And down is good. Surface area to volume is good. So more volume relative to surface area means you're a better cluster. You're a better community. But also algorithmic and statistical tools want that for inferential reasons, right? So you want to go through a low-dimensional space. So if you're a hot dog, how does that plot look? Is it a sine wave? Does it go up? Does it go down? I mean, just qualitatively. So this is an easy question. It may not seem easy because I've come at it a circuitous route, but this is an easy question. But think about it for a minute, because understanding the implications of the empirical results for tree-like properties is going to be important. So this is an easy question. So you're a hot dog. If you like pancakes, you're a pancake. And I want to know the best cluster by this surface area to volume measure as a function of size in the graph.
Is it a two-lobed trigonometry kind of function?
There's certain boundary condition issues that get funny, but if you ignore those, no. So what? Okay, so simpler question I'm asking, the set of nodes that achieves the optimum value in this plot. If this is 1, and this is n over 2, what's the cardinality of the set of nodes that achieves the minimum in a hot dog? N over 2. So here's so the optimum value is here. So down is good, so let's say that's as good as you get. Okay, what about the best cluster of size 1? So I have one node, I have one edge, so that's got to be bad, right? Certainly, it's worse than having, half the nodes, the left half of the hot dog, and a sliver of surface area if it's a thin hot dog, right? So that's a hot dog. The slope depends on whether it's in 1 or 2 dimensions, but it goes down. If you're an expander with no good clusters of any size, you're going to look like that. All right? What do real data look like? So these are the graphs that were in the original SNAP study that we did. These are Facebook social graphs that are a factor of 10x denser. And these are hot dogs. So by hot dogs, these are voting patterns in the U.S. Congress, senators who vote together. And senators now didn't live at the same time as senators 100 years ago, so they can't vote together. So there's a temporal ordering. There's a lot of graphs that have a temporal ordering. So we'll look at this. This is going to be the social graphs that I told you behave very differently in terms of the local global properties. And this is an asterisk on top of that that will be good to know. So for a moment, ignore the slightly denser social graphs. But what you get here is the following three things. So we're defining an extremal metric, right? Remember, this is the conductance value of best conductance of size k as a function of k. These are log plots. So this is log scale. So this minimum is 10, 100, 10,000. All right? We're defining an extremal metric, not obvious that it's robust. The qualitative property of going up or down and being flat is very robust, but relevant to the actual set of nodes achieving the minimum certainly isn't. This is Congress. All right, it goes down. Almost every social graph out there looks like this. Namely, achieves the best cluster of size, say 50 or so, and then the cluster value of the best conductance cluster gets worse and worse and worse. So this is Congress. It looks two-dimensional because we use a visualization that forced it to look two-dimensional, not because it's two-dimensional. These are the sparse social graphs. If you look at the set of nodes achieving that minimum, it looks meaningful. You look at that guy at some cluster that you visualize it means something. You look at this guy, it's something that means something. Now think of an application where it's not you're adding edges in some strategic way because you want to cite people that are friends or whatever, but you're adding edges because Facebook says, geez, do you want to link to this person you haven't seen in 10 years? You say, sure. So you're adding a lot more edges to harvest meta information. You're essentially adding a factor of 10x extra edges, which is essentially noise relative to the generative processes, and red is that. So you just flatten that out. So you don't have any good clusters of any size. All right. What's going on with this? And what's the simplest possible model that will reproduce this? So the simplest model that will reproduce this is extremely, extremely sparse Erdos-Régnier. If you're extremely sparse, you're not even fully connected, then you do have cuts of size log n of log n size. And if you get to a factor of 10x larger, you don't have any good cuts that are 50-50. Extremely sparse. That's true about power law graphs. Now, if you make assumptions like minimum degrees, you've essentially put in a lot more randomness. You destroy that property. Not many people are going to want to do simulations to model real social graphs by using an Erdos-Régnier with 10,000 edges and 10,000 nodes and 30 or 40,000 edges. So you have to be that gutsy to do that. But if you get that gutsy, this is what you're going to reproduce. And the issue is going to be, in this case, you're going to have some sort of core-like structure that means something. And you're going to have little whiskers hanging off. And these whiskers are size log n. They're trees, although trees in a very different sense of the word than we'll get to in a minute, connected by one edge. And maybe by two edges. If you make Erdos-Régnier a factor of log n denser, a 10x denser, you put in enough randomness that you destroy this, and you're flat. All right? So the take-home message is extreme sparsity coupled with a lot of noise, which you might believe is in the real graphs. And we're going to see that as tree-like implications. Something nice you can visualize, something that's messy you can't, some expander thing. You get, I'll grayscale it. You're a hot dog or a pancake. You have some sort of notion of core-periphery. That can mean different things to different people. And you just sort of a sparse graph. Not extremely sparse, but moderately sparse graph. All right, so this is the taxonomy you should have in mind. Now, who cares about this, right? We define conductance and extremely sparse Erdos-Régnier and measure concentration and so on. Back to the example of, two examples. One is you want to know how some disease propagates in your graph. And if the graph looks like a line, and you start your diffusion process here, it takes an enormous amount of effort, lots of iterations to diffuse down a one or two-dimensional thing for isoparametric reasons. You're never going to work, it takes a lot of effort to work the way down. If you're an expander and everything's very well connected, you start here and, what's that commercial that says yellow and blue make green? You take a step or two and it's green. All right, everyone's stepping on everyone's toes. And if you can partition off a not good but, marginally less bad than everything else cluster, it's red. And if I had taken two more steps, that red would have been stepping on the green. All right? Very well connected. Take just a few steps, totally mixing. What if you're at this intermediate regime? So here's one of those whiskers, one of those small guys. Here's another one. Here's another one. Run 3 or 4 steps. It actually takes a lot of effort to get out of that bottleneck of just one or two edges. But here's another guy. And the fact that here's another guy. Now, some one of those edges, you're going to be able to get out slightly more easily. basically because it doesn't take a lot of effort to diffuse out of a 10-node cluster. It would take a lot of effort to diffuse out of a million-node cluster, but a 10-node cluster, you work your way out of it. And once you work your way out of that, if it takes 5 steps, take 5 more steps, you're touching the whole graph. So the time scale to get out of these very small clusters, if it takes some number of steps t, if you run 2t steps, boom, you're going to be touching the whole graph. So there's going to be a sensitive dependency on those 3 types of cases. All right.
Can I ask a quick question?
Yeah.
How do you, you're saying it takes a lot of effort, right? But
Yeah.
how do you quantify effort if you haven't even specified a mathematical model that runs on the nodes of these graphs yet? Like your slide just shows graphs in general, but there's no model that you have provided yet, right?
Good. So I haven't. That's correct. I haven't provided a model for things running on this on those nodes, and that's going to depend on the details of the model. So the simplest one is some type of diffusion, random walk. Now, if you run a random walk, and it's a vanilla random walk, sort of all vanilla random walks are the same, right? Unless you want to get into sort of limiting pathologies, right? You know, you can truncate this way or that way. You can run a random walk out. There's very small things. You can ignore them. If you run a random walk and you set small things to 0, but a good fraction, so if you're on the hot dog and you run a random walk, any random walk's going to be the same, right? It's going to take whatever the t over 2 or root t, whatever, the number of steps to get to the other side. If you run an expand, these sorts of things. But what if you run a random walk and have a little bit of drag? What you can imagine in disease modeling, there's a little bit of drag because you need to get 2 people infected for them to. What if you run a random walk and it's not a vanilla L2 average, which is essentially what a random walk is, but it's the median of your friend's votes, or it's the max of your friend's votes, or it's other things like this. So if you go to max and median, other things can happen. If you go to look at the average of my friends, if you do that, it's even worse. But if you go to my average of my friends and just truncate small things to 0, you're doing essentially a regularization on the vanilla random walk. But that regularization can have a dominant effect. So actually, under the hood in the algorithms we use to generate those plots, we played with spectral algorithms, and it was very important how we dealt with the details of those random walks. So you can take that as a good thing or a bad thing. For a lot of random walks, things will behave in a certain way, but there's a very sensitive dependency on seemingly minor design decisions. So what I'm saying there is true about the mixing, but it's either a good or bad thing. The fact that the graphs are so bad in terms of isoparametric properties means that the knobs that you have to fiddle with the random walk give you a lot of power to diffuse through the graph. And so you can localize spectral computations very locally. So if I want to find you and your 100 closest friends, I can run local spectral computations in size that depends on 100 squared. I don't need to touch the whole graph. And so taking advantage of that dependence is important algorithmically here, and it's certainly going to be important if you want to map this to disease modeling or anything like that, because those drag effects are not second order in this case. But drag effects, I mean, you're talking about something even fancier. I'm just saying run a vanilla random walk. The graphs don't look anything like people are assuming. So figure out what the graphs look like, then try and get fancy. So, but I mean, good point. It's going to depend on a lot of those details. All right, so before I get into notions of tree likeness and the other stuff, are people happy or unhappy or understand, or everyone understands totally perfectly or totally not perfectly? Or okay, one person's happy. And 49, Blair's happy. Okay, so and 48 people aren't happy, but that's good. That's the best sort of. All right. All right. By the time the hour's over, by the time I'm at slide whatever, I'll figure out that I should be pressing the board here. Okay, so what do we mean by tree-like in the context of that taxonomy of 3 things? And knowing that every particular thing is going to be an exception or bells and whistles on that simple story. So the idea is going to be that empirical quasi-randomness, by which I mean there may not be noise. You don't even think there's a stochastic, totally random process as to why you add edges. But unless the reason you add edges on Facebook is like extremely strongly correlated with the reason your mother adds edges on Facebook and her bridge partner adds edges on Facebook and her bridge partner's grandson adds edges on Facebook, unless there's an extremely strong correlation between that, 2 or 3 hops, it's going to be noisy. It's going to be largely uncorrelated. So think of that as sort of noise in the generative processes informally. So quasi-randomness coupled with some sort of structural heterogeneities, degree distribution. It could be geography. Some of these things live on the Earth, but that's a very sort of second-order effect. But it could be important because sometimes these second-order effects are leading order. Can we quantify, and this leads to tree-likeness. So the question is, can we quantify this in a way that's going to be statistically meaningful? Because ultimately we want to make some inferential claims in a way that's algorithmically tractable, hopefully on graphs that have more than 100 nodes or whatever. like the ones we had before, millions of nodes or tens of millions of nodes. And it's going to be ideally useful in a way such that practitioners from the domain from which the graph was constructed can say, yeah, that makes sense, or no, it doesn't, and can do some sort of iterative analytics like that. What does it mean to be tree-like? So large informatics graphs are oftentimes talked about as having tree-like structure. That's an assumption. It's a hypothesis. It's almost never tested. And it turns out to be surprisingly difficult to test and evaluate that in practice. So the bottom line of the second half here is going to be that there is tree-like structure. We have ways to characterize it and exploit it in certain settings. But the ways that are successful in characterizing and exploiting it are rather different than the ways that people typically think about it and think will be useful to exploit. So how do you measure tree-likeness? So I have a graph. Graph has to do with number of, a tree is a graph with no cycles. Let's define a metric over all the graphs in the world. The number of edges you need to remove to make it a tree. I mean, that's a legitimate notion of tree-likeness, right? So that's not a particularly useful notion of tree-likeness for anything, or at least anything that I know, but it's a legitimate notion. So what we want is a notion of tree-likeness that's going to be useful for something. So recall back to the NCP prop graphs, right? So we said as a function of size, you can go down, meaning the largest clusters are better. They can be all bad, or you can go up. So what this is saying is that the cut or partitioning properties of graphs are just very, very different than machine learning tools. The manifold, anything that boils down to a low-rank space. Anything that boils down to an asymptotic limiting property, we're going to concentrate enough so that you stay up here. So the partitioning properties are very different. So let's consider a notion of tree-likeness that measures how tree-like is a graph in terms of its partitioning structure. So that'll be one notion, tree decompositions. So a different notion is how tree-like is a graph in terms of its distance or metric properties. And it's not explicit in this plot, but the reason for this plot has to do with this core-periphery structure, meaning if you go from A to B, you need to go from node through some sort of core to another node. So the metric properties of these graphs are just very, very different than random geometric graphs or other things that might inform people's intuitions. Concentric expanders, where all the distances are log n, essentially. Delta-hyperbolicity is a notion that captures tree-likeness in terms of the distance properties. So the good thing is these sit on top of good theories. So I didn't go into the details, but when we generated these isoparametric profile plots, we used spectral methods and flow methods, things that we had very strong theoretical understanding of, and we could, since the graphs are sufficiently messy and noisy, it was hard to draw a conclusion from any one graph, but we could look at the differences between the two different tools and what they got and be more confident in the claims you're making. So same thing here. So these are two tools with very strong theory. It comes from structural graph theory and geometric measure theory, and so graph theory and group theory. So good theory that you don't want to be a slave to, but might guide some intuition as to what's going on. We're also going to talk about something like K-core decompositions. So this does not capture tree-like structure in general graphs. It'll turn out that these two very different notions of tree-likeness actually capture very similar structures in real graphs that correlate strongly with K-core decompositions. So in the interest of time, let me not go into too many details except to say sort of delta-hyperbolicity captures the notion of tree-likeness in terms of metric properties. And the idea is that, if you're a tree, there's a way to go from A to B, and maybe you have an edge here and an edge here and an edge here, but if the shortest path in your graph is not so different than the shortest path in a tree, then you can say it's delta hyperbolic, where delta parameterizes how short it is. So for example, this might look tree-like. If you have a grid, that's not going to be tree-like because there's a lot of different paths that you can take from A to B that are just going to be very different. The actual metric's going to be very different. So there's a bunch of ways to define this Gromov's 4-point condition and a couple other ways that are equivalent up to constants that actually matter in these applications, but not in theory. Tree decompositions. You take a graph, and I want to construct another graph such that this other graph is a tree, and I basically take all the nodes from this graph and put them in the nodes of this graph. So call these things the bags. And I want to satisfy certain properties. And in particular, what I want to satisfy is that if I take a node and I put it in two different bags over here, that the bags in the tree in between those two bags contain that node. So there's this running intersection property. And what I'll be saying is that I take a graph that's not a tree, I map it to a tree, and you can always do this. I just put every node from the original graph in one bag. So the tree decomposition, I have a bag. It contains every node from the original graph. That's a legitimate tree, right? It's one node. So that's not such a useful tree decomposition, but it's legitimate. So I want to minimize something. In particular, I want to minimize, say, tree width or tree length or something like this, some property of the size of the bag. So I want to minimize the largest bag in this tree, for example. So that's useful for a bunch of things. It's used in sparse linear algebra to minimize fill in certain types of computations. Graphical model, people use it because of the running intersection property. If you have, I guess it's not obvious from this graph, but if you pull out a bag, the left half and the right half do not talk to each other. Right? And so if I want to make predictions about the left half, and the left could be a small little corner of it, I don't need to know the right half to first order. Right? It's just intermediated by this bag.
Do you need any kind of symmetry property of the original graph to make this happen? Like in this example, it looks
No, this is a nice, pretty picture, but no, this will hold for any graph. Any graph I can put in one bag. A different question is if I have some symmetry property. So there's a bunch of theoretical work on tree decompositions that's useful in structural graph theory, not obviously useful in terms of implementations, that have some strong theory. There's a bunch of heuristics that are motivated by the scientific computing applications. Basically, you want to minimize the min degree of the thing you put in the bag, or minimize fill, or something like that. Not obviously useful for social graphs because the exact minimum degree may not matter as much. You might want to capture sort of softer properties. So we're going to be using the existing heuristics and making claims, but an obvious question is, say I have other properties, either symmetry or I want to preserve some core-periphery or local global structure in the tree decomposition. Can I come up with legitimate tree decompositions that satisfy that property that are more related to the noise properties of social graphs or other graphs? And you can do that. That's just done less than these existing things. But yeah, but you don't have to. K-core. So I have big graph. Let's call the K-core basically the set of nodes that's well connected, parameterized by K. So everyone is degree K and is K connected or something like this. All right. So anything could be going on inside that K-core. In particular, the K-core doesn't need to be connected. It's just it could be disconnected. All right. So go through these different notions, and in some cases they're sort of similar. In some cases they're not. So when are they similar and when are they not? So here's an example where they're not. Say I have a complete graph, a clique. In terms of its metric properties, everyone's distance 1 here, but I can construct a graph with a central node and a bunch of edges. Maybe this is an artificial node that I just invented. And now everyone's distance 2, or if I put a 1/2, everyone's distance 1. So this is tree-like, actually, in terms of its metric properties. It's not tree-like in terms of its partitioning properties, right? Just to cut this, I need to cut a lot of edges. Similarly, a ring. So that's not so hard to partition, right? I just cut 2 edges. If I take this ring and squish it down and call these bags and cut there, I have to cut approximately the same number of edges as I had to cut in the ring. So this is going to be tree-like by this measure, not going to be tree-like by this measure, basically because these things are spread out. This is a particular graph, but other graphs you're going to have the same problem. So it's not going to be tree-like by hyperbolicity measure. So it'll turn out that these sorts of dense types of cliques in the rings are going to be sort of extremal cases, and we'll see that appearing in lots of the social graphs. And in real graphs, there's a lot of other stuff going on. These things exist, but more importantly, when you run an algorithm, say a tree decomposition heuristic or something to compute hyperbolicity, and you have a big 100,000 node graph or million node graph or whatever, what does the algorithm glom onto? I mean, who knows, right? If the algorithm is designed to minimize fill or minimize something else, the steps of the algorithm do certain things, and it either finds these things or tries to avoid these things, and that's going to have consequences that will probably be very different when you apply it to a social graph than you apply it to the data for which it was generated. So tree-likeness in toy graphs, a tree is tree-like. If you have, an Erdős-Rényi graph, it's going to be not tree-like unless it's extraordinarily dense, and there's some subtleties. Planar grid's not going to be tree-like. So there's 2 things where you may not be tree-like. And there's 2 different things you need to think about. One is if there's a nice geometry, you're a hot dog or a pancake, because then the diameter of the graph and lots of things depend on essentially the number of nodes, or the square root of the number of nodes, or something like that. Constant degree expanders or random graphs like that have a diameter that's log n. The natural scale to think about those graphs is log n. It's not root n. All right? If something's log n, it's bad. And that's just very different. Now, real graphs do have some, in particular, local structures that look vaguely like that. You and your 100 friends cluster well, so it looks, and you can visualize that in 2 dimensions. So it looks something like that. They have properties like this. So they have properties that look a little bit like both of these, and they have properties that look like this, where the graphs are tree-like or not, depending on which metric you use. Tree decompositions, let me not go into the details except to say there's a bunch of different tree decompositions, and they all do different things. You run a different tree decomposition heuristics. Some it might look like this, some might look like this, some might look like this for a ring. So let me not go into the specifics of what each of those means, except to say we're trying to distill out properties of the graphs that we're looking at, and if we see something that splinters like this, the question is that really in the data, or is that an artifact of the fact that we ran this heuristic versus that heuristic? And we can start to decouple those because the way different heuristics behave on, in particular, the two types of graphs where the notions of tree decomposition and delta-hyperbolicity are different, will in general be different. All right, graphs we looked at. A bunch of random graphs, parameterized by the amount of randomness, from obscenely sparse to just very sparse. Very sparse should be trivial. You expect that. Push the limits, go to extremely sparse. You can do that with flat graphs like Erdotrend. You can do that with power laws. You can do that with, whatever there was something recently that, the RMAT. All of these have a randomness parameter, and if you make it sparse enough, you're going to have results qualitatively like we were talking about. The snap things I was talking about, that's these ones where the profile plot went up. Facebook graphs that are denser, and then a bunch of sort of stuff like planar graphs that's the road network of the U.S. So how are these things going to look like? So let me go to the summary. Before I do that, let me make one point, but then go to the summary. So here we have plotted on the x-axis the core depth. How deep a core are you? On the y-axis is some measure of the number of things at that core as we peel the graph apart. When you're a random graph, and this could be an Erdotrend, it could be a power law, it could be anything. If you have a minimum degree, if you set the parameter large enough, you'll typically find things that look something like this. So the point of this is that all the random graphs are in the 10, all the nodes are in the 10 core, plus or minus 1. And so random graphs have that property, that if you send to the right limit, things concentrate. If you set it to be sparser, it'll look like this. There'll be some things in the 0 core, meaning these little peripheral things, and there's going to be a wide distribution of cores that the nodes are in. So it's not the case that there's enough randomness that everyone in the random graph's in the 10 core or the 5 core. It'll be the case that there's some people in the 1 and the 2 core, some people a bit deeper. So that's going to be a qualitative property. And what does a real data set look like? Here's one of the snap graphs. Now the cores are much deeper here. It's going up to, I can't read that, but it's 50 or something. Whereas the ones I had before, since they were so simple and random, went to 5 or 10. But starts at 0, goes up, and then runs down. So what you see is that the 0th order inhomogeneity in the real graphs is going to be captured by the extreme sparsity. The same thing we saw before, but here we're doing it in terms of the k-cores. So I'll go to the summary. In terms of the numerical values, let me also just point out, this is an example where the profile plot went up, and here's a Texas of one of the Facebook graphs where it was flat. So why the difference? Here, 1% of the nodes are in the deepest cores. Here, nearly 10% more. So qualitatively, they're going to behave similarly, although quantitatively, they behave differently enough that the qualitative properties of the profile plots are different. What's the number of edges leaving the deepest cores? 1% versus 7%. So these graphs have a lot more edges, and a lot more edges means that basically all the peripheral things that are very peripheral, because you've added a bunch more edges, tend to be linked much more strongly to the core. And that's algorithmically going to create a lot of problems.
What's Texas 84? I'm sorry.
It's a Facebook graph from Texas. There was a set of Facebook graphs that were released and then unreleased from the, 5,000 to 50,000 nodes from 100 universities in the early days. This is sort of a typical example for a lot of the collaboration graphs. This is going to be a typical example for a lot of the social graphs, but there's a lot of differences between each of these. All right? All right. The bottom line is that we're going to have delta-hyperbolicity, and tree decompositions in general capture very different manners in which a graph can be tree-like. For realistic graphs, they capture very similar properties. So I didn't go into the details of that, but for realistic graphs, they are going to capture very similar properties. And the properties are basically related to this core-periphery structure. So you can define cores and peripheries in a number of different ways. But think of it as that there's some set of nodes that are marginally better connected than everything else. There's some that are less connected. In terms of the profile plots, we saw that this is what was going on, and these guys are responsible for the small minima. In terms of the tree decompositions, what we'll see is that these guys are relatively better connected bags towards the center, and that to walk from a peripheral node to a peripheral node, you have to walk via the deeper cores. And extremely sparse random graphs with a zeroth order model that will describe these things. All right, so let me now sort of go quickly into exactly what we did with delta, exactly what we did with tree decompositions, and basically that's the summary. But in terms of hyperbolicity, delta hyperbolicity, defined in terms of the 4-point condition, the so-called 4-point condition, the bottleneck here is going to be cycles. All right, if you have a vanilla random graph with big cycles, that's going to be a problem because hyperbolicity, you can't collapse those cycles, so that's going to be a problem. Now, a question is this graph more tree-like than that graph or less tree-like than that graph? In terms of the vanilla delta measure that's used in geometric group theory, they're both the same. But especially if these guys become very long, you might say, squint at this, ignore that. That's more tree-like than that. So let's define a size-resolved version of delta. And the idea of the size-resolved version of delta will be that, and did I make this? So, delta, we've normalized to be 0.5 up there. High means bad. So if you're more tree-like, you go down. If you look at just, as a function of the diameter of this quadruped, if you look at the smallest level, diameter 1, you have these black guys. If you consider something larger, this graph with one thing sticking off, or 2, or 3, or 4, the delta for the highlighted structure will go down. And so by the usual measure, if you choose the max here, these things are all going to be the same. But by looking at a size-resolved version of delta, we'll see this. So what do you see in the real data? In the real data, this is what you see. So there's a lot going on here, and the coloring is not so good. So let me say what we're seeing. So first thing, if you have a hot dog or a pancake, a hot dog's different because it's a line, but a pancake, a 2 or 3-dimensional thing, you're going to go up and you're just going to hit a half. There's a slight fluctuation there for a certain reason, but don't worry about that. So you're not tree-like at any size scale. If you have an Erdős-Rényi graph that's dense enough, you go up and you hit a half and you stay flat. Now, the size scale of how large you get to here on the x-axis and how large you get to here on the x-axis is very different because the diameter of a planar graph, meaning discretization of a planar graph, is very different. It's root n. The diameter here is log n. So quantitatively resolving these differences is actually very difficult on the real data because it's 10 log n or a half log n squared, right? But if you change the sparsity value of the random graphs, what you see is that this thing will pull down. It'll pull down because you've gone from having a fairly well-connected core to having you splinter this, and you're having pieces that stick off just a little bit. These are trees. They're not interesting. But it'll pull this down, and the reason this pulls down, if you actually look at the set of nodes, is that you're going to have paths like that, exactly the same thing we had before.
So what it looks like, so we have the zigzagging up on the top left corner of the plot. Is that different lines superimposed upon one another? Is that one?
There's a certain artifact that's just because we take a min and something has to be divisible like 2 or 4 or something,
like
so it doesn't matter.
cycle in mod 4.
Oh, I see. Okay.
Yeah. So that actually creates a lot of problems if you're looking at this and can only resolve up to there.
Divisibility issue.
Right. Okay. So
Right?
there's the general.
But yeah. So the general trend is ignore that oscillation. But it's hard to ignore it if you just look at one thing on one side. I mean, looking at these things at various sizes makes it clear what's going on. But if you look at one on one side, yeah. You see this in the power. Anything random, we have a parameter that governs how random it is. It'll look that way. The real data. So here's a bunch of here's the autonomous systems, co-authorship, Nutella, something, and one of the Facebook graphs. And they'll go up, and depending on the exact value, they'll have a larger, smaller diameter. And depending on essentially the density value of this, it'll behave that way. The Facebook graphs are going to be much denser, essentially going to be more random and less tree-like by this measure because you have the deep cores. If you pull out those deep cores, they look more like some of the sparse snap graphs. Of course, you throw out half the nodes by removing the deep cores. You might throw out a third of the nodes. You throw out the deep connections. The guys that remain are less well connected. They're more spread out in terms of this core-periphery structure. And you're going to look more like this.
So did you say that the hot dog graph didn't qualify as a good tree-like graph here?
So okay. So in terms of the with the tree-like structure with the delta-hyperbolicity and the tree decompositions we're measuring characterizes tree-likeness. One thing it doesn't discriminate is between the two different types of isoperimetry, because both the Facebook graphs and the Snap graphs will be tree-like by this measure, but they're different in terms of the isoperimetry. So that's one thing that doesn't discriminate. In the flip side, what is discriminated by isoperimetry, but is not discriminated by here, the hot dog case. So the hot dog case is no different than the pancake in terms of the surface area to volume. I mean, quantitatively it's different, right? But both the best clusters are 50-50.
Yes.
In both is the left half and the right half. Hot dogs are trees because they're line graphs,
Yes.
right? Yeah. It's peculiar that anything low dimensional is not tree-like. 2 dimensions, 3 dimensions, 4 dimensions, 5 dimensions. But if you have a tree, if you have a line graph, it is tree-like. Unless, of course, you do have boundary conditions and loop that line back to a cycle, in which case you have this graph that's extremal in these other cases. So a line is an exception. You've got to just be a little careful about the line. And so it's not naively tree-like in the same way. So you just have to be a little bit careful about it.
So for line graphs, the delta decomposition is not a good measure then?
For line graphs, we don't, I don't think have it here, but it would look tree-like. I mean, we would have to deal with the local structure, and I don't know quantitatively the local size of the hot dog might be too thick. I don't actually know what those particular graphs would look like here. So it depends on how long the hot dog is, because there's actually some internal structure on each congress. So I don't know if there's enough that you'd see that with this delta or not. The other thing is delta is actually pretty finicky. Something that I was going to gloss over is if you look at something that sits on the Earth, a power grid,
yes.
that looks the same way as any low-dimensional graph in terms of isoperimetry. But having a few high-degree nodes, power stations or whatever, actually makes it look, pulls it down at larger size scales. So delta is a very non-robust measure. And so how exactly it would behave, I'm not sure because of that non-robustness.
So in that case, tree decomposition is a better measure?
So the bottom line from what we're going to be talking about is tree decompositions of the winner. And they're going to be more useful. And then maybe the winner just because we haven't figured out that they're bad one step beyond. But certainly a delta is problematic because of the non-robustness. And tree decompositions, all the evidence is that with the existing tree decompositions we can do stuff. But if you had heuristics that were more aligned with what the social graphs are doing, that would be better still. So they probably would be better. All right, so let me wrap up. The theories sort of... So this is sort of a hierarchical. I like this result, right? So here, this is one of these hierarchies, right? So this is a binary tree right here. People talk about hierarchies of binary. That's a binary tree. What if I add edges between, levels on each binary tree? If I add edges like that, that thing is the Poincare disk up to some small distortion. That thing is quasi-isometric to the Poincare disk. So that thing is a tree in the soft sense of the word. So that seems like a good model for saying, can we add randomness as it's added in common random graph models and get something interesting? And the short answer is no. The short answer is no because there's two things that happen in sparse graphs when you pass the log n over n threshold. One is that the graph becomes fully connected. Two is that the empirical degrees become equal to the mean degrees up to small fluctuations. You need a model to bifurcate those two. And so basically, the way people add randomness in real graphs adds too much global information. And so you mess up the large-scale loops and the large-scale cycles and damage all the local structures is the short answer. More work to be done there, though, I think, to justify that. So let me just present a couple pretty pictures on the tree decompositions and not go into those other results. And the pretty pictures are going to be these. So there's going to be two things that you'd want to do in the... Now, let me show you these pretty pictures. So the tree decomposition can do two things. So a tree decomposition will give you a tree regardless of the graph you give as input. So then you have to look at the internal structure of the bags or the structural properties of the tree to say, does this mean anything? And there's been two cases where we've seen that you get something useful. One is when you take something like this. So this is one of the Facebook graphs. And So you have, this is actually a peculiar one, but we've seen in other ones also. So you're going to have deep cores. And these largest bags are fairly large. So the tree width of all these graphs is bad. But the graphs have a structure such that the bad bags sort of provide a scaffolding on which other stuff hangs off. Where you want to make predictions, inferential predictions, is not on the deepest cores, because that's where your information is least reliable. It's going to be out here. So if you want to do link prediction or edge prediction, predict, say, the dorm that someone's in this university, you might say, I have a bunch of plus labels here and a bunch of minus labels elsewhere. Can I make a prediction? And it turns out in a bunch of cases, I don't know how good your eyes are with the color coding, but this is a red to blue plot, and there's more red here than out there. So the bags are localized imperfectly on sort of more peripheral things. And this is true even though these graphs don't have the nice network profile plots in terms of the isoperimetry. So these are capturing something in terms of the core-periphery structure. It seems localized on, in this case, meaningful ground truth communities, even though it has sort of weaker diffusion properties, better connectivity properties than you'd like. So that's a very local thing. This is the tip of the iceberg. You can probably do more with that, but the tree decomposition is capturing something you'd expect. The second thing is at large size scales. And so at large size scales, in a lot of cases, you see something like this. These bags are all the same, up to a few edges here and there. All right, so a node can be in many bags. And so if you look at this bag versus this bag versus this bag versus this bag, there's very few changes between the bags. Now, clearly, as you go all the way along this, they change a lot. The color coding here is, are you a freshman or a sophomore or junior or senior? So this is a very macroscopic notion of community, a very weak notion, in fact, right? And it's a notion that's very bad in terms of its isoperimetric properties. It's not the case that there's good surface area to volume. So this is a community that is very different than people think, than satisfies the informal properties of communities that people think about. But the large-scale structure of the tree decomposition is capturing this. So there's been work on message passing and label passing algorithms that find the large-scale structure of geographic clusters in Facebook graphs. And presumably it's capturing it for reasons related to this. So what's going on here is, remember the profile plot of this thing looked like this. All the clusters are bad, of any size. So all these clusters are bad. All these bags are bad in terms of their surface area to volume. So how is it the case that we're finding something meaningful? How is it the case that the label propagation algorithms find something meaningful in terms of the large-scale Facebook graphs? Presumably it's because they're finding clusters that are just marginally less bad than all the other clusters. And they start with a seed set of nodes. And they start here and they run a few steps. The exact dynamics is going to be important. The label passing algorithms do not do a vanilla L2 diffusion. They do something more like you pass around labels and take the max of the median of someone. And they'll glom onto something here. And they'll say, listen, cut that out, cut that out, cut that out. That's Europe and Africa and Asia. And that's essentially what those algorithms are doing here. So this has captured the large-scale structure of these tree decompositions.
How do you define this side?
So this is actually the last slide. I was going to put up a conclusion slide, but I'm going to have to go about 8 slides ahead because I swapped those other ones before and after. So I can wrap up with this and skip the conclusion slide because the conclusion is, are there any questions or something?
All right. Let's thank our speaker. Okay, are there any questions? I do have one burning question. There is something you said that's fundamentally counterintuitive. You said that, for instance, in describing this FD Caltech thing, you say that the cores are not very informative. But you also mentioned earlier that basically a lot of the peripheral stuff, you can view them as basically added edges that may be noise. But then you said those are more informative in terms of prediction and things like that. I cannot put the two and two together.
Yeah, I mean, I can't fully. Most machine learning and statistics methods, they need to get capacity control to make predictions. So there's a couple ways to do that. One is to go through a low-dimensional space. You do the pancake thing, you cut here. Predictions here are unrelated to predictions there except for that interface. So that's the way most of the machine learning and sort of statistical results work. So you can get that with peripheral things. Facebook, it's trickier because the peripheral things are reasonably well connected still because that factor of 10x edges. Heuristics. If you're 2 hops from a high degree node, don't do that hop. So a lot of people do heuristics like that, and those heuristics essentially engineer in a bias towards the periphery, which will engineer in a stronger inferential basis for that sort of thing. So that's for local things. So if there's good clusters, quark conductance, this thing you need for inference, they're going to be small. Now, there's other cases where it's a useful thing to predict which continent someone's, the IP address is from. And so even if the clusters qua the conductance measure are bad, so you don't want to call them communities in some sense of the word, except some trivial sense of the word, it may still be good to make that prediction. And so the question is, can you find them? And in that case, you want the large-scale stuff. So there's just a lot of random edges in the large-scale stuff, and it's going to be hard to make those sorts of predictive claims. What's going on with those things is essentially that you have some large-scale structure. To first order, it's just this random mass. To second order, there's some underlying geometry. And so if I start with a random mass, I see it in different places, and I don't run one of these label propagation algorithms a million steps, but I write a new paper to say balanced label propagation by putting in a balance constraint, or by engineering in the balance implicitly, which is both of those have been done. Then I can, or I can just run the label propagation algorithm 3 steps. I don't run it. It's not like it's like running a random walk 3 steps instead of a million steps. You get something that's more strongly biased towards the initial conditions. You can sort of refine that local initial seed set. And so if you do it right, with some engineering, you can pull out fairly large clusters, half dozen clusters, each of which is half dozen graph size over half dozen, all of which are not very good by this particular objective, but which certainly are marginally better than some random set of clusters, which is just going to be bad. And the fact that you get something so informative from a set of clusters that's only marginally better than bad is significant, because that's saying you're trying to tease out just a little bit of signal from gobs of noise. And the flip side is here, I'm trying to find small clusters. There's gobs of noise. Can I pull out these things with some engineered local spectral method that deals with the surface area in a much sort of more sophisticated way? So in both cases, if the 0th order description of these things is sparse and random, and any local structure of you and your 100 friends, you're not sitting in a nice hot dog or pancake. You're sitting in this extremely sparse, extremely noisy, bad place. How are you going to engineer the algorithms to pull that out? So I think both at the small size scale and at the large scale, that's what you're trying to do. You're not in some nice asymptotic regime. The sort of asymptotic models that people have are sufficiently far from what these graphs look like that, at least so far, most of them aren't a useful qualitative guide to understanding what's going on. But can you sort of implicitly engineer out these sort of regularization properties? Yes, that's what I meant by that.
One more quick question. Yes? Could you share with us over the last 5 years what science problems you've been working up to and where you see the next 5 years?
Me or the world?
You.
Me.
Aren't you the world?
I'm the world. It's funny you say 5, because about 5 years ago we started going into more detail on these. So these were, what we wanted to do then, these graphs haven't gotten larger in the last 5 years. Other people's have, and other people have looked at larger things. I haven't, partly because, we didn't, 5 years ago we couldn't say what was going on. And if you want to get larger, you can get larger to 100 million nodes or something. If you get larger, and you do with memory management and all sorts of stuff, it's a mess. So at least what I've done is, work 10,000 to 50 million. So you're in RAM. You can't do stupid things, but you can develop algorithms. So now we're sort of at the point where, in parallel with that, I've done different hat, a lot of stuff on randomized matrix algorithms, and scaled those up from teeny to, we can run least absolute deviations on a terabyte of data. So real parallel distributed stuff. So now the question, looking ahead, merge the two. The sort of framework for graph algorithms is you can think of certain types of computations. If you're doing a diffusion, it's sort of like a matrix vector multiply. If you're doing a label propagation, it's sort of like a matrix vector multiply, except you're taking a max. It may not matter in RAM, but if you're going to go larger to something, well, either worry about flops in RAM with multiple cores or try and go larger. The computation is not going to be the expensive thing. The communication is. You need to structure the algorithms, the details, the weeds of these local spectral methods in a way that will scale up and do that at size scale 50 million. So we're almost at the point where we could begin, a good enough understanding of what's going on here to scale those up. So, what does that mean? Say a factor of 1,000. There's not many graphs that are a trillion nodes unless you're in a very specialized place, right? But you can get billion, and larger with 10 billion or 100 billion edges, and those are either public or semi-public, whatever. So that's something that I think would be reasonable. Now, of course, I don't know what a machine will look like in 5 years. It may be the case that RAM is an uber byte in 5 years, and so these things fit on your cell phone. So that's another thing that's hard to figure out how these things will evolve. But that's scaling up to something where The other thing is when you're extremely large, it's not clear these sorts of qualitative analytics is what you want, right? I mean, cut out a piece, do qualitative analytics on 100 million nodes, or 100,000 nodes is pretty small, and people have trouble with that, right? So get that understanding there, get better features, engineer this in, and then scale that up in a system. Because the people that have these, extremely large, meaning trillion or whatever, that's probably the soft spot there. So, factor 1,000 larger, but and wet it with the matrix algorithms that we already have scaling up.
All right. If there are no more questions, let's finish our speech.